This is a reaction depicting the overall transformation when we do the nitration of benzene using nitric acid. And nitric acid here, sometimes you see this written, well, more often than not, you see it written as HNO3. They're showing it here how things are really connected, and it's this nitrogen-oxygen bond here right in the middle that is the breaking point when this thing reacts, because what actually adds to the ring is our nitro group that is actually in the form of a nitronium ion. That's the electrophile here that eventually adds to the ring. The sulfuric acid is mentioned as a catalyst because it helps break apart that nitric acid molecule to create that nitronium. And the other examples of electrophilic reactions that we saw earlier involve something similar, where we create a positively charged atom or group of atoms that ends up adding to that ring. The percentage here that you'll often see quoted for reactions just tells us something about how well that reaction works. 95% is the percent yield of this reaction, which is pretty good. That's one reason nitration reactions have been studied so well. They work really well. What we're going to start to deal with now is the effect of doing reactions like this on a substituted benzene ring, a benzene molecule that already has a substituent on it. That greatly affects the rate at which these reactions occur, and it also greatly affects the position of the incoming electrophile and which isomers form when you have two substituents on a benzene ring. For example, in this figure here from your book, we see a comparison of plain old benzene in the middle and two common substituted benzenes. On the left, the trifluoromethylbenzene, and on the right, the methylbenzene that we call toluene. And what we find is if we do nitration on these molecules, if we add an NO2 group, we find that compared to benzene, the molecule on the left with the CF3 group is much slower, about 40,000 times slower in its reaction rate compared to benzene, whereas toluene is faster than benzene by a factor of about 20 to 30. So we use benzene as our standard of comparison, but it's inevitably true that if you already have a substituent on the ring and then you try to do something like nitration, you're going to find sometimes the reaction rates are greatly affected. And what will go along with the difference in reaction rates are also a big difference in which isomers you form, because if you already have something substituted on the benzene ring, you add something else, you have the possibility of the ortho, meta, and para isomers to form. For example, in this slide, if we take toluene and do nitration on it, it works very well. And those are the three possible products that we could have, assuming that we are limiting to this to mononitration so that we only get one NO2 group. If you change the reaction conditions, the amount of nitric acid you're adding, you can get dinitro and trinitro products, but here we're going to assume that we only get one of these three possibilities. And if we didn't know any better, we might imagine we would get all of these in decent amounts. But if you look at those percentages, you see that whereas we get a lot of the ortho and a lot of the para, we don't get very much meta-nitrotoluene. That tells us this reaction is not a good way to make that meta-isomer. We don't get very much at all. We might suppose that we would get a lot of the ortho in the sense that there are two positions available, two hydrogens, either one of which we could remove to create that ortho isomer. If you look over here at the structure for our reactant here, toluene, we've got hydrogen to the left of that methyl group and another hydrogen here to the right, and either one of those can be removed to give you an ortho isomer. So we've got two opportunities to do that. The para, down at the bottom, there's only one hydrogen that can be removed to make that product, so we might not be too surprised that we get less of the para isomer. But the meta position, there's two positions that are meta to that methyl group, so we might suspect that we would get the same percentages as same percentages of ortho as we do meta, but yet there's this big difference. So clearly there's a preference for making ortho and para isomers, but not very much with meta. And that's typical of any alkyl group that's on the ring. It's not something special for the methyl group. If you have ethyl, propyl, tertiary butyl, any alkyl group attached to a benzene ring, the nitration tends to give you significant amounts of ortho and para, but not much meta. And we're going to talk about why that is the case after we see a few more examples.